Thank you for the introduction, and thank you for having me speak. So yes, my result, or the result I'll be presenting today, are estimates for Carleson norms of dyadic Carleson sequences. So this work involves Bellman functions, which is a relatively recent method for proving sharp or best possible estimates for various function classes. So the Bellman function for a particular inequality will be the solution of the corresponding extremal problem. So either finding the largest locally convex function on a domain in Rn subject to some boundary condition, or the smallest locally concave function, again, subject to some boundary condition on a domain in Rn. Usually the difference of two convex sets. So if this function is obtained, then both the sharp constants and optimizers, which are functions or sequences of functions that support the constant, follow. So I'll be presenting a problem which demonstrates Bellman functions in a dyadic context, specifically when estimating the Carleson norms of sequences that are defined in terms of dyadic A2 weights. And this work is joint with my PhD advisor, Leonid Slavin. So we'll begin just with some definitions and notation. So for an interval I, we denote by this angle bracket the average over I of a function with respect to the Lebesgue measure. And for a fixed dyadic lattice D, we say that a non-negative sequence indexed by the elements of this lattice is a Carleson sequence if its Carleson norm is finite. So the Carleson norm is just the supremum of weighted sums taken for over elements corresponding to sublattices of the lattice. So our Carleson sequences will be defined in terms of dyadic A2 weights. So we've seen Muckenhaupt weights, AP weights a lot in this conference, but just to recall, they're almost everywhere positive functions that have finite dyadic A2 characteristic, which is defined below. It just says that the supremum of this product of integral averages taking over elements of the lattice is uniformly bounded. So now we'll introduce the main objects and our goals. So for phi, a non-negative increasing function on the interval 1 to infinity, we can define a sequence indexed by the elements of a lattice D as follows, right? So in terms of some dyadic A2 weight W, right? So for an element of the lattice, we define the corresponding term as follows. So we see that phi is a function of this product of averages, and then we have this kind of term that's symmetrized in W and its reciprocal. So here, delta J is to stand for the difference in the averages on the left and right halves of J. All right, so our objective is to find the sharp upper estimate for the Carleson norm of such sequences in terms of the dyadic A2 characteristic of the underlying weight, which define them. Right, so in other words, our objective is to find the best function K phi, which satisfies the inequality below. So the sharp lower estimates are also important, but we'll be focusing on the upper estimates. Leonid Slavin investigated this, and he had a nice clean theory for the lower estimates, but the upper estimates had created some interesting situations. So the most common situation when encountering such sequences is the case when phi is a power function, right, for a positive power alpha. So such sequences arise when estimating dyadic pair products on weighted L2 and have been used with suboptimal estimates in ingredients and proofs by Beznesova, Mraz, and Perea, and Whitwer. Vasily Vystunin also studied a similar sequence in the case when alpha is 0 and W is an A infinity weight. And a few years ago, Leonid studied the general sequence using Bellman functions, and here was his result for the upper bound. So he'd found that if phi is increasing and this function psi, so defined, which is phi of s squared over s squared, is convex, then if q is some value of the characteristic for the dyadic A2 characteristic of a weight, then the corresponding k of phi of q is given by this expression. So the Carleson norm would be bounded for that corresponding weight would be bounded by this expression. So for the situation when phi is a power function, we'll write k alpha. So K alpha, again, would be the best function which satisfies this inequality for all dyadic A2 weights. So you found that this best function K alpha is given by this expression here, this piecewise expression. And you can see that there is a particular range of alpha missing from this definition, namely alpha between 1 and 3/2. And this is because the function psi, which we recall the definition here, happens to not be convex. And that's a key ingredient in his proof. So we've been able to cover this gap for all phi with concave psi, but we've needed to add additional assumptions of regularity and the derivatives of psi being alternating in sign. So if we denote by Rj the jth successive midpoint from 1 to root q, we have the following for the result. So if psi is C4 on the interval 1 to root q, such that psi and psi double prime are concave and increasing, then that best function K of phi is given by this expression, right? So we can compare this to the situation for phi, K phi when psi is convex, right? So instead of this integral here, we have this kind of weighted sum. And as a corollary, we were able to cover the range for that for the alpha between 1 and 3/2, right? So we obtain K alpha as being given by this expression. So just to kind of get an idea of kind of like our new result as compared to the old result, we can graph the dominant terms for each expression for large Q. So for Q large, the old result gives that K alpha is approximately this here, and the new result gives that K alpha is approximately given by this expression in orange. And so we can graph the coefficients of these dominant terms, and we see that indeed they have the expected behavior, right? So for the range of alpha between 1 and 3/2, our result gives an optimal estimate. And then of course, for alpha outside of this range, the old expression applies and gives the correct estimate there. So the method of proof follows the standard Bellman approach, which is to refine the original estimate that's over the entire function class. So in this case, dyadic A2 weights with characteristic at most Q, when you're interested in computing this best function K of alpha or K of phi at Q. So you want to refine the estimate over the entire class into estimates over subsets parameterized by so-called Bellman variables. So these Bellman variables are just functionals on the class that kind of sort them according to the values that they take, right? So E of phi is parameterized by an x here, which is just two possible values for our Bellman variables. And the Bellman variables in this case are the integral average of the function over I and the integral average of its reciprocal. So the Bellman function is a function of these parameters and is defined as the supremum of this expression taken over all functions in the corresponding class, right? So x is x1, x2 here. So the collection of all these valid parameters forms a planar domain. It's the region bounded by the curves y equals 1 over x and y equals q over x. And once we found this Bellman function on this Bellman domain, then K phi of q will follow. So how do we find this function? How do we find this Bellman function? So we begin by deducing certain properties that can be found from its defining expression in the underlying class. So the most essential of which, and is one that you'll find in most applications of Bellman technique, is the main inequality, which is either some concavity type inequality or convexity type inequality, depending on whether you're considering an upper Bellman function, right? You're considering an upper estimate or a lower estimate, a lower Bellman function. So here, this takes the form of just some midpoint concavity, right? So this says that for any 2 points in the Bellman domain, such that their midpoint is contained in the domain as well, we have this inequality holding at those points. And then we have homogeneity, which just says that the Bellman function is constant along hyperbolas contained in the Bellman domain. And then the boundary condition, which says that along the lower hyperbola, the Bellman function is identically 0. And this is because all functions in the corresponding classes are constant almost everywhere. So those are the properties that we're looking for candidate functions. So say we found a candidate function, how might it relate to the actual Bellman function, the true Bellman function? And so we have a theorem called Bellman induction, which says that the Bellman function, right? So if you have another function on the Bellman domain that satisfies the boundary condition and the main inequality, then it majorates the Bellman function, right? So that is to say the Bellman function is the smallest function on the domain, Bellman domain, satisfying these two properties. So we prove the opposite inequality by providing for each point in the Bellman domain a sequence of admissible functions, so function of the corresponding class, that support the value of this candidate function, right? That is to say, such that the limit of that expression in the definition of the Bellman function tends, for these functions in the sequence, tends to the value of that candidate at that point. So we call such sequences optimizers or optimizing sequences. So by homogeneity, we can reduce our focus to the line segment, this line segment here in the domain. So we can construct our functions. We can think of we can construct any candidate function as a function of one variable, which will then extend to the domain. And we're also able to reduce verification of the main inequality to just two inequalities in one variable. So we have that the main inequality is equivalent to the following two conditions, right? So the normal main inequality, which is akin to the standard main inequality on the domain, just for x plus and x minus that are on this line segment. And then we have what's called the tangential main inequality. So if you verify these two inequalities for your function as a function of one variable, then you have the standard main inequality on the entire Bellman domain. So the standard approach is to conjecture that whatever this function that we're constructing satisfies, this candidate function satisfies the main inequality with equality when s plus and s minus are very close to one another. So this produces a differential equation. We then solve this differential equation and then verify that the solution satisfies the main inequality for all pairs, not just s plus, s minus that are infinitesimally close. So this approach works well when phi is increasing and size convex. The normal main inequality coupled with the boundary condition gives an ordinary differential equation whose solution readily follows. And the verification of the main inequality for this candidate works when size convex. So the tangential main inequality also produces a differential equation, and that function works for the case when phi is decreasing. However, when psi is concave, the solutions of these differential equations both fail the normal main inequality. So we have the normal main inequality when psi is second differentiable is equivalent to this inequality here. And we can see that this clearly fails when psi is concave. So this means that the Bellman function does not satisfy the main inequality with the equality for infinitesimal splits. And so this ends the standard approach for explicitly computing the Bellman function. So instead, we need to construct a special Bellman majorant via a non-infinitesimal splitting procedure. And then we show that this satisfies the main inequality and actually equals the Bellman function at a special selection of points in the domain by providing optimizers for those points. So here's a description of our candidate. If we denote by square root of q L, we can define a sequence of functions an on 1 to L as follows. So let S be some point in the left half of the interval 1 to L. And for k greater than or equal to 0, let Sk denote the kth successive midpoint from S to L. So for some n, for a fixed n greater than or equal to 1, we define an simultaneously at the points sk from 0 to n as a solution of the linear system below. So this is a system with n+1 equations and n+2 unknowns. And so it defines an at each L, or at each S in this interval, up to its value at L, right? Since every S is contained in such a system. For S equal 1, we set the value at 1 of this function to be 0. And we solve the corresponding system, and this then fixes the value at L for every other system. And so that defines our intermediate function for all S in 1 to L. So this procedure assumes that points split to the far end point in the normal main inequality. So we just then define our candidate to be the pointwise limit. And so we obtain this expression here, where Rk corresponds to the sequence Sk when S is 1. So here's just kind of a visual illustration of the splitting procedure as it defines these intermediate functions. So we see that system corresponding to S equal 1 in magenta, right? So we have the system of equations defined in terms of these points. We fix the value at 1, that fixes the value at L, and then we have the, say for an arbitrary point in the left half of the interval 1 to L, S, right? We have that corresponding system. And so now we just read the value that was determined from the first system, right? And then we can solve for these points, for the value of the function at these points in blue. So the optimizing sequence for each Rk, so we're able to construct optimizing sequences for these magenta points, right? So the optimizing sequence for each Rk is defined recursively in a manner that's similar to the case for infinitesimal splits. So if delta n is as defined here, then the nth optimizer for the Rk from 0 to n and L are defined conjointly, right? So the nth optimizer at R0, which is 1, is just the constant function 1. And then the optimizer at Rk is defined, the nth optimizer at Rk is defined as a concatenation of the nth optimizer at L and at Rk minus 1. And then at the optimizer at L, the nth optimizer at L is defined as this kind of concatenation of the scaled optimizer at Rn. Right, so this just gives a recursive definition for the nth optimizer at Rk. So here's just kind of an illustration of these splitting procedures, or these splits in the Bellman domain. So here we have our two hyperbolas that bound the Bellman domain, and we can see that each Rk splits to its previous neighbor and then to L, right? And then at L, we split back tangentially onto Rn. So each of these functions in the sequence, in the optimizing sequence at Rk, can be expressed as the limit of a sequence of simple functions. And so we do so here. It's kind of, and this is for the sequence at L. So it's kind of hard to understand what's going on here. But we can illustrate the sequence for the first term in the optimizing sequence at L here, right? And so we can see kind of how these functions have a lot of self-similarity in their definitions. And this is just the sequence that approximates the first term in the optimizing sequence at L. So we're still in the process of understanding how these extremal splits generalize to other concave psi. And we also hope to understand how to extend these results to all increasing phi, which would potentially involve meshing different splitting procedures, so infinitesimal and non-infinitesimal splitting procedures together on the domain, and also tackling such estimates for sequences defined for other AP classes. So, and that's all I have. Thank you.